All right, so this lesson is speed and velocity. It's lesson 3 for the first unit on kinematics. Now, technically, this course only has the first unit as dynamics, which is chapters 1, 2, and 3 in your textbook. But that's a big unit. So what I do is I break it up into sort of kinematics, which is chapter 1, which is all on motion. Right? Things like speed, velocity, your 5 equations for uniform acceleration, both in 1 dimension, 2 dimensions, projectile motion, and what's new in grade 12 in this unit is we're also going to talk about relative velocities. Okay? And then chapter 2, which is more dynamics, which is talking about the forces that cause motion. We'll be going over them, creating free body diagrams. And chapter 3 is going to introduce circular motion. So objects that are undergoing circular motion and what forces cause that. So let's start with this one. Speed and velocity. So I want to go over a few terms. And without reading them, okay, when I mention these terms, just pause the video. I want you to think about them, see if you can define them and compare them yourself. So first two, scalar quantity and vector quantity. So pause the video, define them, and even give a few examples of each. All right, so scalar quantity is something that only has magnitude. For example, speed, 5 meters per second, 40 kilometers an hour. Energy is a great scalar quantity, right? 40 joules, 100 joules. Right? Charge as well, 1,000 coulombs. Time, okay, 8 seconds. Vector quantity is one that has both magnitude and direction. So speed becomes velocity as a vector. So velocity would be 100 kilometers per hour north. Okay, force is a good one. 10 newtons east or 100 newtons down. Okay, another one is position and displacement. Those are both vectors. And those are also the next two words I want you to try and define and compare yourself. So think about them. Position and displacement. What's the difference? Pause the video, think about it. All right, so position is where you are relative to some point of reference. Okay, so let's say you have this point here, and you're over here. Okay? You can say that you are, I don't know, for example, 1 meter, there's no way that's 1 meter, but 1 meter to the right, or if this is your coordinate system, where that's north, you can say 1 meter east of that origin point. That's a position. A displacement really is just a change in position. Okay, so we write a displacement like this, where d is position. So change in the position, which is a vector quantity. And since we're comparing our positions from where we are now to where we were before, you would say it's our final position minus your initial position. So if you did start here, and then you moved over here, right, in that case your position would be 1 meter east of the origin, and your displacement would be 1 meter east of the origin. However, they're not always the same. If you start here and move over there, let's say that's halfway. Well, your position is 1 meter east of the origin, but your displacement was only half a meter east of the origin. Notice that we could make them the same simply by changing where our origin actually is. And essentially what you're doing then is forcing our initial position to be 0. Okay, but that's the difference between position and displacement. So what about distance? How does that factor into everything? Pause and think about distance. All right, so distance is actually a scalar quantity. It just means how far you've traveled. So for example, if you're here and you travel here and then you travel back, let's say half a meter, total distance you traveled was 1 meter. Remember, your displacement is comparing your positions from where you are now to where you are before. So your total displacement, since you finished and started at the same place, your displacement is 0. Okay, so the big difference is one's a scalar, one's a vector. Okay. Well, what about speed and velocity? Think about those two terms. right? So same thing. One is a scalar, one is a vector. Speed's a scalar, does not have a direction. Velocity is a vector. All right. Well, how about average velocity and instantaneous velocity? What's the difference there? Well, this is actually very, very important. So let's say we had a graph. Let's make this a VT graph. We'll talk more about time graphs in a couple lessons, but you probably remember them from grade 11 anyways. Let's make a nice straight line there. So this says, well, our velocity, we started at 0, and it's increasing at a steady constant rate. Now, if you wanted to figure out your average velocity, right, you can just take velocity here, velocity there, right? Add the two, divide by half. And you can find your average velocity, right, which would be probably somewhere over here. Now, your instantaneous velocity would be your velocity at any point in time. So what's your velocity here? Or what's your velocity here? That's the two big differences. Your average has to be between 2 points in time. For example, between here and between there. Whereas your instantaneous velocity is at a single point in time. So for example, your speedometer when you're driving in your car, what does that tell you? Instantaneous velocity or average velocity? Well, it tells you instantaneous velocity. It'd be pretty useless if it told you average velocity, because you could go on a road trip and drive for 5 hours, reach your destination, stop, and then look at your speedometer, and it might still be telling you you're driving 99 kilometers per hour. There's no real useful way of using that kind of information. So it tells you instantaneous velocity. All right. Now, vector addition and vector subtraction. This is very important. When you're adding vectors, you cannot just add their magnitudes. That only works if the vectors are in the same direction. So, for example, let's say I have 1 meter and 1 meter. Yeah, in that case, I can say total is 2 meters. But if I have 1 meter and then 1 meter, total is not 2 meters, it's 0. And you came completely back. Your total displacement, which is the sum of all previous displacements, is 0. Okay, so that's easy in 1 dimension, right? In 2 dimensions, what if I move 1 here and 1 here? You can't add that either. Your total displacement is not 2 meters, right? This is a nice triangle, so you'd have root 2 and a nice 45 degrees. And so if you're using your compass coordinate system, you can say your total displacement is root 2 meters, or 1.4 meters east, 45 degrees south. Okay, so that's what you would have to say. So when you're adding vectors, you always add tip to tail. For example, if you have these two vectors, and you just take tip, connect it to tail, like that, and that's your total. So this is A and this is B. This might be C, which is the sum of A plus B. Okay, well, what about subtracting vectors? I usually find people don't like subtracting vectors. Adding them tip to tail is a really easy rule to remember. Now, subtracting vectors, if you really don't like subtracting vectors, then add them. It sounds weird, but think of it this way. Let's say here you have vector A, and here you have vector B, and you wanted to subtract them. Well, the negative of vector B is the same magnitude, but opposite direction. So I can now write this as vector B, and I can simply do A plus that vector negative B, which is the same as A minus B. And so I can add now, simply tip the tail for this vector would be A plus negative B gives you C, which would be A minus B. Okay, so that's just a quick review of how you would subtract vectors. So now that we've gone over that, let's do some sample problems. Question 1 is more like a grade 11 problem, but we all need to sort of review this. So here we have a truck driver reacting quickly to an emergency, applies the brakes. During the driver's 0.32 second reaction time, so let's write our known values, our given values, 0.32 second reaction time. The truck maintains a constant velocity of 27 meters per second. So we have a velocity of 27 meters per second, and I'm just going to write forward. What is the displacement of the truck during the time the driver takes to react? Okay, so in this case, there's no acceleration. So displacement is simply velocity times time. If you can't remember that equation, dimensional analysis is a great way to figure it out. But let's say I make a mistake. And I say, oh, displacement is velocity divided by time. Look at your units. Do they make sense? This would be meters per second. Divided by seconds, would give you meters per second squared. Those are not the units of displacement. Something's wrong. That equation's wrong. And you'll know right away if you think about the units to see if they work. That's what dimensional analysis is called. So we do velocity times time. Okay, well this is meters per second times by seconds. Oh, seconds canceled, you're left with meters. It works. That's very important. It doesn't really mean that the equation is true just because the units work out, right? For example, if you remember, kinetic energy is 1/2 mv squared. Well, the units would work out if I changed that 1/2 to 1/16. That doesn't mean it's right, but dimensional analysis is a good hint to tell you it looks like you're on the right track. Right? It'll certainly tell you if you're wrong. All right, so getting back to this, you can write in our velocity, 27 meters per second forward, multiplied by time, 0.32 seconds, and you get 8.6 meters forward. Wow, that's 8. That's a real funny 8. 8.6 meters forward. Okay. So make sure, again, this has proper significant digits. We started with 2 and 2, so we should have 2. If one of them was 3, we should still have 2. Remember, you always take the weakest link. Units, and since it's a vector, direction. Okay, significant digits, unit, direction. All right. Question 2. Now we're getting on to 2 dimensions. Here we have a skater on Ottawa's Rideau Canal. Travels in a straight line 850 meters, 25 degrees north of east, and then 560 meters, 21 degrees east of north in a straight line. The entire motion takes 4.2 minutes. Question A, what is the skater's displacement? Question A is the big one. Question B, once you know question A, is really quick. Finding the displacement is the big one. Displacement is a vector, so you cannot simply take 850 plus 560 and be done with it. No. So let's look at our 2 vectors. Our first one is 25 degrees north of east. So there's east, and north of that by 25 degrees. And that is 850 meters. Okay, this is north. Okay, let's write the other one on a separate grid. This one is 21 degrees east of north, so this way, where that is 21 degrees. All right, so those are our 2 vectors. This one's 560. And we need to add them. Now you can simply connect them, okay, tip to tail, and then you can figure out what that total displacement is by using sine law or cosine law. You can't use your trig ratios because that does not make a right triangle, but you can do it using sine and cosine laws, which is something you will do in the calculus and vectors course, the vectors part of it anyways. I'm going to stick to components. The reason I'm going to stick to the components is because in physics, components is helpful because you're not always simply adding 2 vectors. If you're adding 3, 4, or 5 vectors, then you have a really weird shape there. It's not a nice triangle. You can make 4 or 5 triangles out of it and use sine and cosine law 4 or 5 times, but now that's just getting tedious. Okay. There are questions where sine and cosine law certainly is easier to use than components, but you learn that in calculus and vectors. And so it's very important that in physics you use components, and in calculus and vector you use sine and cosine law, so that you have both tools on your belt. That way, whenever you come across an unknown problem, you'll understand which one is easier to use. So let's do this using components. To do that, we need to do a few things. First, take our vectors, split them into components. You can't just split them into components unless you actually choose a coordinate system. You can choose any coordinate system. I could say, oh, that's north. And just completely mess you up. Okay, but I'm going to choose our north direction to be our positive y direction. Again, I could have made this our positive y direction. But again, why would I? Right? There are some problems where that makes the problem easier, but not in this one. And therefore, east, I'll make our positive x direction. Now that we have a coordinate system, which you should always write, okay, and then you should stick with your coordinate system throughout the problem. Now that we have that, we're going to split every vector that's not parallel to either our x or y into x and y components. So this one's going to have an x and a y, and this one's going to have, now you could do it like this, or you could do it like this. It doesn't matter, right? This x vector is the exact same as this one, it's just translated to a different location on your grid. But its direction and its magnitude are identical. It doesn't matter where it's placed on the grid. So you can either use 21 degrees here to help you solve it, or you can just do 90 minus 21 and use this angle if you prefer to use the angle to the x-axis. Doesn't matter. I'll stick with 21, and I'll simply say that our y component, which I'll write over here, is 560 times the cos of 21, and our x component, which is up here, well, I'll write it down here actually, it is 560. Okay, since it's opposite, it'll be the sine of 21. Alright, so there's our x and y. We'll write the same thing for this one. This one, your x is going to be 850. Since it's adjacent, it's cos 25. And this one's 850 times the sine of 25. If you're not sure how I'm getting those, I'm sort of skipping a step because we've done this a lot in grade 11. But just to review, I'll review this once with you. Okay, if you do the sine of 25, sine of 25 for a right angle is opposite over hypotenuse. The opposite side is our y component, and our hypotenuse is 850. Multiply both sides by 850, you get 850 sine 25, which equals our y component, which is why I wrote that value next to our y component. Okay. Oh, once you do components enough, you'll just be able to just write it like that. So now that we have that, what we can do is add up all of our y components and add up all of our x components. Because these two vectors, I'll try to show you why this works. If you are to connect this vector to this vector, tip the tail, you would have your 850 plus your 560, and that would give you your total displacement vector here. All right. Now if you split these, drop my pen, you split these into your x's. This has an x, this has an x, and of course this one has an x. But you'll notice this one plus this one equals the x value for our total displacement. Similarly, this has a y, and if we add this y, you get the y for your displacement vector. So what we're doing is we're going to take our x and add our x. You add those two x vectors just like you do here, and we'll know the x vector for our component of the total displacement vector that we're looking for. If we add the y, this y, and this y, then we'll know the y for the total displacement vector that we're looking for. So essentially, what I'm trying to do, in order to figure out this total displacement, I need to find its x component and its y component. And then once I have that, it's simple. You have a right angle triangle. You use Pythagoras and the tan ratio, you can figure out exactly what that is. So let's do that. Let's first add them up to figure out what your total x is. So our total in x is going to be 850 cos 25 plus 560 sine 21. I'm running out of room, so when you do that and you punch that into your calculator, you'll get the total in x to be 971.1 meters. Okay, and it is going to be positive, meaning it's in our north direction. Then you do the total in y. Okay, so you have this one, 560 cos 21, plus this one, 850 sine 25. You do have to remember that they do have a direction though. In this case, it's kind of easy because all of our vectors are in the positive directions that we've chosen. However, for example, if this was down instead of up, we would have to subtract it. Okay? But in this case, we're adding 560 cos 21 plus 850 sine 25. When you do that, you get 882.0. Now I know that I should only have, was it 2 significant digits, and I've written 4. You should always keep a couple extra in intermediate steps. You don't have to write anything in the proper significant digits until your final answer. All right, so now that we have those are our directions for x and y. So here is 971.1 and 882.0. And we're looking for what that hypotenuse is. So to solve, we can say this is our total displacement, which is a vector, and I can put an absolute value around that, which pretty much states I'm searching for the magnitude of that vector. And to do that, we use Pythagorean theorem, which is the square root of 971.1 squared plus 882.0 squared, and you get 1312 meters. Which, when I'm completely done and I state my final answer, I will write as 1.3 times 10 to the power of 2 meters. We also need to figure out the direction, theta. So tan of theta is opposite over adjacent, so 882.0 over 971.1. Take the inverse tan. Make sure your calculator is on degrees, not radians. I get a lot of students coming from math that have it on radians and they get the wrong answer. So make sure it's on degrees, and you should get 42 degrees. That being said, we can now write our answer for A, saying the total displacement is 1.3 times 10 to the power of 3. And this is 42 degrees, so east, 42 degrees north. Then part B says, what's the skater's average speed and average velocity? So what's the difference there again? Well, speed is a scalar, velocity is a vector. Now, velocity is easy to calculate because we already have the displacement. We just calculated that. Now, when I do the calculation, I'm going to use my couple extra digits, 1, 3, 1, 2, over the time is 4.2 minutes, so do 4.2, put it into seconds, so multiply by 60. And don't forget, this does have your direction here as well. So you'll get a velocity, an average velocity of 5.2 meters per second east, 42 degrees north. So that's how you calculate average velocity. But how do you calculate average speed? Remember, speed is a scalar quantity. So it's going to be our total distance over time. Distance is also a scalar quantity. To figure out that, you just, well, add the distances. In this case, we actually are going to do 850 plus 560. So we'll do 850 plus 560 meters divided by the time, which was 4.2 minutes. Turn it into seconds, so multiply by 60, and we'll get 5.6 meters per second. Alright, so that's your difference between speed and velocity. Speed is distance over time, velocity is displacement over time. Alright, so tomorrow's lesson we're going to go over acceleration and our 5 equations of uniform acceleration. And we will also do a question of acceleration in 2 dimensions as well. But it's going to be the exact same method of adding components.